think we have an announcement.
I'm Kara. Doesn't really matter though. The HBSD, if you're wondering what that stands for, doesn't really concern you unless your name is Stephen Dillon, because it's his birthday and he's in this class. So that's just really exciting. I'm not going to point him out because that's just embarrassing. But that's what HBSD stands for. Yeah, clap. Thanks. Thanks for your time.
Happy birthday. When you get to my status in life, you're not so eager to count these things out. Now, we shall establish foundation for being able to dive into and understand the nuts and bolts of acid-base chemistry, Bronsted-Lowry acid-base chemistry, reactions in which H phosphorus change. This diving in process begins with writing correct principal system inventories for whatever acid-base containing system we are considering. And from that, write correct equations for any acid-base reactions which occur within the system which is constructed. And after we get through this, we will be ready to tackle the analysis of Bronsted-Lowry acid-base systems from a quantitative standpoint. Equilibrium analysis. Not only recognizing what you have, but how much. And when we finish with the establishment of these considerations, you will be able to take any water solution system and analyze it to the extent of being able to report a correct QPSI for that system. That's pretty powerful. You now can take any water solution system from an acid-base standpoint, which means any species in the system whose presence depends on pH. And as I said, find out not only what you have in the system, but how much. That's pretty powerful. It'll take us about a couple of weeks to get through all this. How we begin. To begin, we complete developing our ability to write correct principal system inventory. We started this in discussion class. We talked about this last time. And so, in order to have this rather complete, I've rewritten that part of our PSI consideration from the point of the system being an aqueous solution. Something prior to this, look at your substance. Your substance is itself. Inventory is as itself. Aqueous solution of strong Bronsted-Lowry acid. Strong Bronsted-Lowry acid is hydronium ion, and then the acid stronger than hydronium ion. The table tells you this. Since any acid stronger than hydronium ion will react on being dissolved in water to an extent of practically speaking 100%, a water solution of such will inventory as hydronium ion, the conjugate base of the acid in water. Example which we've already looked at, hydrochloric acid solution. Principal species inventory, system inventory, hydronium ion, chloride ion water. Weak Bronsted acid. Bronsted-Lowry acid itself. Because the main difference between, as we have chosen to define such, a weak Bronsted acid versus a strong Bronsted acid is the weak acid does react with water to make hydronium ion. That's why it's an acid. But it reacts to a limited extent. unlike the strong acid, which react practically to an extent of 100%. This causes us to realize something that's very important. In the water solution of the strong acid, does equilibrium exist between the solute acid and water? No, because all the acid dissolved went away by reaction. But in the weak acid, you betcha. Keep your mind on that when you do any chemistry. You've got to pay attention to that when you do any chemistry with the water solution of the weak acid. The PSI reflects that. The acid itself, water, and counter ion if the weak Bronsted-Lowry acid is ammonium ion compound or a solution of a hydrated metal ion. Now remember, I try to write formulas so that they keep with structure. That's why we're here. What I'm doing is continuing with this list. If we pay attention to PSI for aluminum nitrate solution, you've got to recognize an aluminum ion, like all other metal ions, which have appreciable positive charge densities. Practically speaking, this will include all metal ions with a charge of +2 or +3. There are only a very few metal ions found to show a charge of +4, and they never stay as hydrated metal ions. The reaction extends with water is too extensive. Exception, strontium ion, barium ion. Those are +2 ions, but they're very large. The upshot of which is that they have not particularly large charge densities. You can get them to form defined hydrates, but the acidity of these defined hydrates, the strontium ion and barium ion, is so weak that practically speaking, we don't have to pay attention to them as Bronsted acid. The same applies to hydrated calcium. You'll recognize such, or better recognize such, when we talk about KAs, ionization equilibrium constants. Equilibrium constants which numerically represent the strength of an acid. Ka for hydrated calcium ion is very small. More on that later. And of course, equilibrium. The solute acid on reaction with water. Other examples, 1 over acetic acid, PSI, acetic acid itself in water, ammonium chloride solution. Ammonium chloride is an ionic compound. So like all ionic compounds, when you dissolve this, you wind up with ammonium ions and chloride ions. The solution will also show itself to be mildly or weakly acidic. Because in the presence of ammonium ions, which reacts with water, make hydronium ion and ammonia, but the extent is small. So the principal system inventory is ammonium ion itself, chloride ion, and water. Sodium hydrogen sulfate solution. Hydrogen sulfate ion is an interesting Bronsted acid, because more often than not, Bronsted acids are positive ions, like hydrated metal ion, like hydronium ion, or neutral molecules, like HCl, like acetic. But hydrogen sulfate ion is a negative ion, yet it has the capacity to a measurable extent to react with water to produce hydronium ion and sulfate ion, the conjugate base of hydrogen sulfate ion. Any of you have any familiarity with hydrogen sulfate ion by way of chemistry that you might do at home? You ever use or observe your folks use materials such as Sanaflush or Vanish? Good porcelain device scouring agent. If you go to Publix, you can buy either. I suggest you buy the Sanaflush. It's the same stuff, but it's cheaper. So you have an advantage. People spend more money on advertising. Of course, they share that. Soup. Often, for example, in Florida, we get carbonate deposits or phosphate deposits. These types of deposits are readily scoured by treatment with hydrogen sulfide ion, because the hydrogen sulfide ion will react with the carbonate effectively, with the phosphate effectively, and destroy the insoluble carbonate scum or the insoluble phosphate scum. Regarding hydrated metal ions, some of you may well be curious about how do I know it's 6 water molecules? Well, we'll talk further about that when we get to chapter 23 and spend time discussing properties and structure of these metal ions, like hydrated metal ions. Depends on size and depends on charge magnitude. But for now, practically speaking, all hydrated metal ions, at least the ones with which we shall be concerned, will be hexahydrates. That's not an explanation, but it will at least remind you how to get the formulas for these things. The only exception of consequence is hydrated silver ion, which is a dihydrate. But hydrated silver ion, like hydrated calcium ion, is such a weak acid that, practically speaking, its bronze-set acid strength can be neglected in water solution. So we can just as well write this ion as this. But if you're going to explain the acid, bronze-set acidity of the hydrated metal ion, you've got to write the formula as a hydrated species. So that's where the H pluses come from when this stuff reacts in acid. And one more thing, I think I mentioned this to a couple of you folks previously, regarding my desire to write these formulas so as to keep with structure. This is a pictorial representation of aluminum ion placed in the vicinity of a water molecule, which is exactly what happens if you take an ionic compound like aluminum nitrate and dissolve it in water sulfur. The aluminum nitrate dissociates, like all ionic compounds, and you now have aluminum ions and nitrate ions. Well, what do you think might happen, electronically speaking, between this aluminum ion with a substantial positive charge density and non-bonding electron density on a water molecule? You think there's a natural attraction here? Because this is a region of negative charge. This thing is rather substantially positive. Upshot, significant attraction. And that's how these metal ions get hydrated. So I write the formula for the hydrated metal ion like this because the bond formation interaction is between aluminum ion and the oxygen end of the water molecule. That's why I got the formula written like this. Because the oxygen, the water molecule, aluminum ion bonds are all involving the oxygen end of each water molecule that's part of this cycle. Strong bronze-to-Lowry base. Either a hydroxide ion compound or a compound of a base that's stronger than hydroxide ion. To simplify matters at this stage of the game, I've only included in our acid base table 3 strong bases. Hydroxide ion itself, sulfide ion, and oxide ion. That's enough. PSI, hydroxide ion, conjugate acid. Water, counter ion at the source of hydroxide ion is an ionic compound, like sodium hydroxide. Dissolve that, have sodium ions and hydroxide ions in solution, as well as water, of course. Example, 1 molar potassium sulfide. This I believe we talked about yesterday. Wednesday. Ionic compound. So number 1, I have to realize, dissolve this in water, dissociates. This puts K plus AQ and sulfide ion AQ into solution. I put quotes on the sulfide ion AQ because this doesn't stay there. Why does this not stay there? Because this reacts with water, as I believe we just discussed last time, to produce the conjugate acid of sulfide ion and the hydroxide ion, keeping with our inventory. Extent, practically speaking, 100%. Which is why if I have a water solution in the laboratory, and this is that solution, are there any sulfide ions in there? No. So if I write this formula to correspond or attempt to describe any chemistry in which this stuff participates, I'm writing a lie. It ain't there. What is there? HS minus and hydroxide. Weak Bronsted-Lowry base. Bronsted-Lowry base itself, again, the equilibrium game applies. Because weak Bronsted-Lowry bases react with water to produce hydroxide ion, but the extent is limited. So, the principal system inventory will be the base itself, water, counter ion at the source of the base of the ionic compound. Here are examples. 1 molar ammonia, probably the most common weak base other than water itself. PSI, ammonia, and water. 1 molar sodium acetate. Ionic compound, sodium acetate. Dissociates into sodium ions and acetate ions. Acetate ions, I should imagine at a glance, you recognize to be the conjugate base of acetic acid. But acetate ion reacts with water only to a very tiny extent, making you a mildly basic solution. 1 molar sodium acetate has a pH on the order of 8. Very mildly basic. So PSI, acetate ion, water, and counter. And a directive now, since we've now laid the foundation for writing these reaction equations. In an aqueous solution of weak Bronsted-Lowry acid or weak Bronsted-Lowry base, keep this in mind, this is what we mentioned as we discussed the water solutions of the weak acid or weak base. Equilibrium involving a solute acid or solute base. Weak Bronsted-Lowry acid, weak Bronsted-Lowry base. Reacting with water exists all the time. And with the ammonia solution. Example. This is the principal Bronsted-Lowry acid base equilibrium, which is alive and well, which exists in the 1 molar ammonia solution. This accounts for why the solution is basic. It accounts for the fact that ammonia is a base. But again, what's the difference relative to strong base? Reaction extent, small. And we'll find that reflected by the value for the equilibrium constant for this reaction, which we'll be talking about next week. Now, one question which some of you got to in discussion class, some of you didn't. It's just an attempt on our part to be sure that you've understood what we've talked about here. Because I know that practically speaking, even though I did introduce you folks to some of this stuff in 2045 laboratory, assignment 5, that you're seeing this for the first time. And I repeat, it's damn important. Because if you are going to do and understand chemistry occurring on a system like a water solution, you can't do that if you don't know what's in the system. Then you can do and understand the chemistry, which may take place in the system. What kind of compound is this? Ionic or molecular? Ionic. Practically speaking, I trust you did this in 45. If you're looking at a binary metal-nonmetal compound, or even more practically, any compound which contains a metal metallic element in its composition, treated as ionic. There's all kinds of exceptions to that, but we'll not talk about the exceptions now. Wait till we get to chapter 23 and 24. Then we'll talk about the exceptions. So if we treat such compounds as ionic, including ammonium ion-containing compound, which you can recognize by the formula for the compound, because you see the H4N formula as part of the compound. Those are ionic compounds. When they are dissolved in water, they dissociate. Now, from an acid-base standpoint, after we consider putting the component ions of the compound in solution, like we did with K2S, where we started with a solution of potassium ions and sulfide ions, we have to answer the question from an acid-base standpoint. Do either or both of these ions react with water after they've been put in water by dissociation? How can I find out? I use the acid-base thing. Use this information. That's why we developed it. And students often ask, well, what about K+? Does this do anything from an acid-base standpoint? What about Na+? The answer is no. We made a remark which is in regard to that just a short while ago. We said treat metal ions which are +2 or +3 as those which form divine hydrates. With the divine hydrate of metal ion accounting for acidity of the solution as such. But +1 ions, the only +1 metal ion that I know of that will form a hydrate that will show measurable acid properties is a hydrate of lithium ion. Not surprising, because lithium ion, of the metal ions derivable from the 1A elements, is the smallest. So it's got the highest positive charge density. And if any of these are going to form a defined hydrate, certainly it's lithium ion. But we don't have hydrated lithium ion in the table. And we don't have hydrated potassium ion or sodium ion in the table because they don't form defined hydrates. They have no impact. Potassium ion or sodium ion, for example, in water solution have no impact on pH. So does this do anything further after it's put in solution? No, nothing. But the other ion is oxide ion. And our acid-base table tells us that oxide ion is even a stronger base than sulfide ion. So to what extent does oxide ion react with water to make hydroxide ions? 100%. So our principal species inventory for this solution is clearly K plus AQ, hydroxide ion AQ, and water itself. Now with that, you should be able to get at the quantitative aspect of how many moles of each of these creatures you have in there, because I've given you the solution volume in addition to the molarity. So, for example, if I want moles K+, all right. Now let's do it this way. 2 mole K+ per mole K2O. Formula for K2O. How do I get a handle on moles of K2O dissolved as solute in this solution system? Look at the molarity. Which tells me this. Remember, molarity is moles of solute per liter volume of the containing solution. Well, what is the volume of this containing solution? .25 liters. And now I can get moles. You do the arithmetic. And when you do this arithmetic, I hope you don't need this thing. And do the arithmetic now to get at moles of hydroxide ion and moles of water. Before you do the arithmetic, how do you think moles of hydroxide ion will compare to moles of potassium ion in this solution? Will moles of hydroxide ion and moles of potassium ion be equal, or will moles of potassium ion exceed moles of hydroxide ion, or will moles of hydroxide ion exceed moles of potassium ion? Three possibilities exist. I want to know how moles of hydroxide ion in this solution will compare to moles of potassium ion from a one or two significant figure standpoint. Equal! Because a mole of oxide ion reacting with water makes how many moles of hydroxide ion? 2! And on we go. Bronsted-Lowry acid-base reaction, page 1850. And you will see on page 1870, question 1810, which provides to you a number of challenges to rise to this task of writing correct equation for acid-base reaction. And prior to page 1817, specifically the discussion that's on 1860, are a number of examples to show you how to play this game. But, again, I have written on page 1816 principal species inventory and quantitative principal species inventory rather than principal system inventory. We want to change it to system inventory. Species is correct here, but the principal system inventory covers all cases. Here are the rules. They're on page 1850. The right equations for acid-base reaction. Inventory. Take the PSI. Without this, you can't do this. It's impossible. Number 2, examine the inventory. Use the acid-base table as necessary for support. You don't have this thing memorized, nor do I expect you to memorize it. But me, I see this thing in my sleep. Happily so. This is pleasing to me, pleasant, relaxing. Use the acid-base table as necessary to select from the PSIs which you have written the strongest Bronsted acid and the strongest Bronsted base. Because if any H plus exchange reaction occurs, if I mix, for example, a solution of a Bronsted acid with a solution of Bronsted base, the acid-base reaction has got to involve the strongest acid in appreciable amount or concentration, giving H plus the strongest base in appreciable amount or concentration. Nothing unusual about that. And then, determine extent. Large or small. We've already to an extent looked at this extent business. That's how we got at these PSI. Strong acids react with water. When they dissolve in water, extend. 100%. Weak acids, small extent. Same for the bases. And when I rewrite the notes, which I'm working on, it's a very time-consuming process. This statement is intended to help those who often make the error of writing reaction equations where we wind up with products, as indicated by this reaction equation, which are materials that can react effectively with reactants. Reactions don't go like that. I'm not going to make something in a reaction system which has the capacity to react to a large extent, which is with something that's in the system. That's contrary to the development of stability. We'll take a look at examples of such as we proceed. Let's proceed. Going now to page 1817, question 1810. You have this. I'm not going to write it on the board. Pure HCl gas is bubbled into 1 molar nitric acid solution. What do we do first? PSI. HCl gas is HCl gas. That's it. Pure stuff. Not hydrochloric acid solution. Now you tell me and I'll write it. The PSI for 1 molar nitric acid solution. Rhodium ion AQ. Nitrate ion AQ. Water. There we have it. Use the table as necessary. From these PSIs, they will be the strongest acid. What is it? Here it is. Is this not a stronger acid than hydronium ion? Look at the table. This table. Or the one that's in the notes. Either will suffice. You remember the acids are listed in order of increasing strength from bottom to top? Do you see that this table tells you that HCl is a stronger acid than hydronium ion? Which you already know, because when you make hydrochloric acid solution, to what extent does the HCl react with water? 100%. So now you're adding HCl, the stuff itself, to a solution which contains these things. And what are we looking for from this collection of these things? We're looking for the strongest base. Which is it? How about that? Isn't that interesting? Nitrate iron's got a minus charge, but water is still a stronger base. Chloride iron's got a minus charge, but water is still stronger base. How else is it that nitric acid or HCl could react to some extent? If this statement was not true. So what we're really looking at for this mixture is the production of a form of hydrochloric acid solution. It's not just hydrochloric acid solution, but the nitrate ion in there. Now comes the last part, extent. The extent rule is simple. You look at the reaction equation which you have written. In your mind's eye, you identify the reacting acid, the reacting base, the product acid, the product base. Remembering that the reacting acid will always convert to its conjugate base. And the reacting base will convert to its conjugate acid. And then you use the table, the acid-base table, and compare the strengths of the reacting acid and the product acid. Or if you wish, if you always get the same answer, the strength of the reacting base to the product base. Bearing in mind that if I've written a reaction equation which shows the conversion of a stronger acid to a weaker acid, does this do that? Yes. Do I expect this to proceed to a large extent or small extent? Because when I go from a stronger acid to a weaker acid, I'm on the path to significant increase in stability. Large extent, you betcha. And that takes care of that. Now we look at the next one. Next one is 1 molar HCl solution this time, mixed with ammonia solution. Tell me. PSIs. There's a hydrochloric acid solution. PSI ammonia solution. There it is. Ammonia weak base. So here's my PSI. Here are my PSIs. From this list, I pick my strongest acid. What is it? There. From this list, I pick my strongest base. What is it? And now, as fast as I can write, I recognize this is the reacting acid, this is the reacting base, so this thing is going to lose H+, and that H+ is landing on this thing. So there's my product acid, the ammonium ion, and my product base, good old water. Extent? Large or small? Large. Because hydronium ions are much stronger acid than ammonium. So extent, large. And now we go to case 3. Sodium hydroxide solution with sulfuric acid solution. Now before we do these inventories, let me make a remark to you about sulfuric acid solution. You notice that the molarity on this sulfuric acid solution is 1. We will, like toward the tail end of next week, well, maybe we'll get to it next week when we got the lecture class next week, unless you'd like to be here on Monday, because I will be. You will find out that depending upon the molarity of sulfuric acid solution, hydrogen sulfate ion, which is the conjugate base of the sulfuric acid molecule, does not in water solution behave as a base. As the base table tells you this. Hydrogen sulfate ion is a base, a weaker base in water. So how the hell is this thing going to get in the game? Well, not only is it a weaker base than water, it's grossly outnumbered by water because water is a solvent. But how about hydrogen sulfate ion behaving as an acid? Does hydrogen sulfate ion behave as an acid in water solution? You want to go back to center, flush, and vanish? You want to go back to our inventory up there? You're damn right. Statement. At fairly high molarities of sulfuric acid solution, the principal species inventory will be hydronium ion and hydrogen sulfate ion in water. But when we get that solution sufficiently diluted, hydrogen sulfate ion will also react with water to an appreciable extent. And then we can have a solution which will also contain sulfate ion as a principal species. In fact, if it's sufficiently dilute, sulfate ion will be a principal species and hydrogen sulfate ion will not. But 1 molar is fairly concentrated. So for the sulfuric acid solution, 1 molar, our PSI will be, as we just mentioned, hydronium ion, hydrogen sulfate ion in water. And I purposely write hydrogen sulfate ion formula like this, as opposed to HSO4 minus. If I write HSO4 minus, and I ask you to give me a structural illustration of hydrogen sulfate ion, like the Lewis picture, I'll bet most, if not all of you, will show me a species where hydrogen is covalently connected to sulfur, because that's what the formula implies, doesn't it? HSO4 minus. And you'll be wrong! So the hell with that formula. And the hell with textbooks that write it that way. And double hell with the authors who write that junk. Is everybody knows that. I said, like hell they do. These are the people that are trying to learn. These are the people that need to learn. You're not talking to people who've already been through chemistry class time and again. Your job is to communicate, and you're failing at that. You know what those textbook authors would do if they took my exams? Flunk! And I laughed. Dumb bastards. Sodium hydroxide solution. Sodium hydroxide, what kind of compound? Ionic. It's a salt. Not one you want to put on your hamburgers. So? Sodium ions hydroxide is what? Strongest acid? Hydronium ion. Strongest base? Hydroxide ion. Understand? Now I'm going to ask for the extent quantitatively expressed. Can you tell me the numerical value which corresponds to the extent of this reaction? One over kW, isn't it? Right? Because water plus water making hydronium ion hydroxide ion is the reaction for which a special equilibrium constant has been tabulated and labeled as Kw. 1.0 times 10 to the minus 14. So for this reaction written this way, K is 1.0 times 10 to the 14. Does that sound like large extent? It's only 100 trillion. Yeah, that's large extent. Now, look at this question. Because you're told that two equations are required. Because you're told that these solutions have identical concentrations of 1 molar each. But you've got twice the volume of the sodium hydroxide solution, don't you? That means from a mole ratio standpoint, when you make this mixture of sulfuric acid solution with sodium hydroxide solution, what is the mole ratio of hydronium ion to hydroxide ion? Hydronium ion to hydroxide ion, mole ratio. Hydronium ion to hydroxide ion. 1 to 2. So after this reaction has proceeded, practically speaking, what we have succeeded in doing is murdering all the hydronium ion in the system. But we still got a bunch of hydroxide ion in here. In fact, half as much as what we started with. So now we've got to be a little bit more careful with this analysis. Look back at the PSI. Anything else in the PSI with which the hydroxide ion will react effectively? If so, what is that species? Hydrogen sulfate. How about? Extent? You betcha. Hydrogen sulfate ion is a much stronger acid than water, and hydroxide ion is a much stronger base than sulfate. The acid-base table tells us this. We'll pick it up in this one next time.